to cover the Chapter 7 in this amount of time isn't possible, so I'm just going to give the gist of each of the sections. Proving trigonomic identities. What you want to do is you want to copy this page and understand that these are essentially truths. They are proven. You don't have to prove them, but you must use them, especially something like this, and something like this, and especially this one, and this one, and even the double angle and addition formulas, but mostly the Pythagorean identities and quotient identities. You must use them to prove other things that are sort of hidden. So, some of these I'm not going to do, and some of them I am. Just to give you an example of how to do them in the time frame that we have. And then I'm going to go back and do this chapter properly, because I've really done an injustice to it. So the first thing you always want to do is take a picture of your identities and keep them handy, because you will always be referring them. So I'm going to keep them maybe on a separate page here and just grab them as I need them. But you will always need to know these identities and to use them. So we'll keep them handy. And we're going to go back to the questions. Sine x is equal to cos x is an identity. Right away you can say that immediately that's not true, because you know the sine graph doesn't look like the cos graph if you overlap them. And he's only using one identity to prove it, which is 45 degrees. He's saying since these are the same, they must be the same. But the 45-degree triangle is the only time cos and sine will be equal. And that's because there's 45 degrees up here and 45 degrees down here. So if you take the sine, and that means their sides are going to be the same. And if we use if we square that and add them together, we're talking about the square root of 2 over here. If you look at if you say the sine opposite over the hypotenuse, okay, but the adjacent over the hypotenuse is the same number. And that only happens with 45 degrees. So therefore, this is not a proof of a bigger experiment saying that the sine of any one will be equal to the cos. If anything, the ultimate truth is the sine of any degree, call x, is going to be equal to the cos of 90 minus x. And it only holds true when sine is 45. It ends up that cos of 90 minus 45 is also the cos of 45. That's why that holds true. But if you were to say the sine of 30, it's only true when you take 90 minus 30, 60. That's the truth. So this is a truth right there. But his logic is not a truth. If you're not going to graph, right trigger, no, we're not going to do that. Give the appropriate functions to match the expression on the left. Okay. So they're in 3, what they're teaching you to do is to rewrite it to match a trigonomic function. So let's look at sine x times cot x. Try to remember that tan x is sine over cos. So cot x is going to be cos over sine. If I replace cot, so that's what cot is, cos over sine. If I replace it, if sine x times cot x, if I replace the cot x with cos x over sine x, I can see that my signs cancel out. See that my signs cancel out. Because this is on the denominator, and this is on the numerator. So therefore, sine x times cot x is equal to cos x. And that's the truth. That's the equivalent. So we can see that over here at C. You can see that right here. So that's the one that matches A. So it's C with A. And then if we look at 1 minus 2 sine x squared, we can see that matches this over here on our truths. Right, let's see. It's going to be in our double angle somewhere right there. That cos of 2x is equal to that. 1 minus 2x. 1 minus 2 sine squared. So we want to bring that over and say, okay, where do I see that on the right? Where do I see cos 2 sine on the right? And you might not see it, but this is familiar over here as well. We discover that there's another truth over here, that cos 2x is also equal to, right there, cos 2x, cos 2 cos squared minus 1. So they've kind of done a double whammy. So since cos x squared is equal to 1 minus 2 sine x squared, and cos 2x is also equal to this, it's fair to say that this is equal to that. So we can see that this, D, matches B, because they're both equal to cos 2x. Then this, you can say, okay, well, what does that match? Well, you really have to expand that to understand it, because it's tempting to say, oh, that's equal to 1, because it's sine x squared plus cos x squared, but it's not. If you expand it, the first thing is sine x squared, right? Sine squared x is how they do it. The next one is sine x times cos x, and then the next one is as well. So you're left with 2 of them. And then the next one is cos x squared. So you're really left with cos x squared x plus sine squared x plus cos squared x plus 2 sine x, which happens to match. And you might say, well, how does it match this one? Well, right away you have to say, okay, well, wait a minute, sine x squared plus cos squared x is this identity, the ultimate Pythagoras identity right here. Since this is a truth that we know to be true, we can replace anywhere we see sine squared x plus cos squared x with 1. Therefore, C is equal to B, which of course leaves the last one as a given because we've matched all the other ones. However, you should try to understand why. Why is that going to be equal to this? For that, we have to go back to our truths and find this right here. And we have to say, okay, that's fair enough. Sine x squared is equal to that. So I can replace this with that. But how do I get to sine squared plus cos squared plus tan squared x? Well, we've just established down here that the ultimate truth is that sine squared x plus cos squared x is equal to 1. And there's 1 right there. So that means I can replace 1 wherever I see it. They're kind of getting weird with how they do it, with this. And that is why sine squared x is equal to sine squared x plus cos squared x plus tan squared x. So they're kind of mixing and matching their truths. 4. Prove algebraically the expressions you match in question 3 are equivalent. I just did. Give a counterexample. Well, you'd have to multiply them out. It doesn't matter. Give a counterexample to show that each equation is not an identity. Give a counterexample to show that these equations are not identical. Well, this is impossible. You cannot have one cos x squared, cos x equal 1 over cos x. And in reality, in your truths, we've already been shown that cos x is equal to 1 over secant x. Therefore, since this is truth, this cannot be. As well, this cannot be truth because we've already been given as a truth in the addition formulas that this is truth. Well, if this is truth, this cannot be. This cannot be. We've also seen in the addition formulas that this is actually this right here. That is actually this right here. Well, if that is cos x minus y, it cannot be the same as sine x plus y. So those are disproven truths. This, we already know from the truths, is this. Where is it? 1 minus tan squared. 1 minus, where are you? Well, we know this is true. So we might as well use this. So there's no way that this can equal secant squared. We can easily prove that by saying, okay, tan squared is sine squared over cos squared. And that 1 is the same as sine squared plus co squared. If we're to subtract them, we have to put this all over co squared and multiply it by co squared. Well, actually, that might not even be the easiest way. You can multiply, both sides by it and prove it. Let's prove the one that can be proven. Why is this true? Why is this true? Well, tan squared is sine squared over co squared. Secant squared is 1 over cosine squared. If we multiply both sides by co squared, it disappears on the right. And on the left, it becomes co squared times 1 is co squared. And co squared times sine squared over co squared cancels out, becomes sine squared. And we know from the Pythagorean truths that this is a truth. That's why 1 plus tan squared is equal to secant squared, not 1 minus. So there's those. Graph the expression. No, I'm not going to waste time doing that. I'm trying to race through it to give other chapters to show how you do these things. Prove this. Okay, prove 8. Prove this. You got to prove. Prove is a big part of the quizzes. And you're essentially going to go back and compare it always to your Pythagorean, to your truths. We're going to skip 7. Prove that this left side is equal to right side. Okay, prove left is equal to right. And to do it, you're often going to have to either break down the right or break down the left. Well, if I multiply both sides by this, I prefer to work both sides. But if you multiply both sides by this, it's going to disappear on the left side. It's going to disappear on the left side. So you're going to get rid of it. So now you just have to prove that the right side is equal to this. Okay. Since this is over 1, we don't have to worry about the bottom. 1 times 1 is 1. 1 times code x is code x. Minus tan x times that is minus tan x. And finally, the most interesting one, minus tan x times code x. Well, tan x times code x is the same as tan x times 1 over tan. So they'll cancel out, and you'd be left with 1. So we're left with this, 1 plus code x minus tan x minus 1. The 1's cancel out. So you're left with this. If you put that over, okay, good. We're left with code x minus, now we've got code x minus 1 at the bottom. Let's multiply both sides by code x minus 1 and get rid of it on the left. So now you're left with get rid of it on the right. So now you're left with this on the right and this on the left. We take this and we're going to multiply it by this. Well, I missed it. God damn it. So now I got to go all the way back. Oh, we're left with this, yeah. So now you're left with this on the right. Now we're going to take the left and we're going to multiply it by this. Well, 1 times code x is code x. 1 times minus 1 is minus 1. Plus tan x times code x is plus 1. And tan x times minus 1 is minus tan x. So you're left with this. Code x plus 1 minus 1, or actually minus 1 plus 1 minus tan x. Well, these cancel in the middle. And now you got left is equal to right. You can do it without going left and right. Some teachers require you stay on the left and prove it on the left. Now you can do that if you want. It's a little bit more complicated. Geez, how would you do it staying on the left? Yeah, I think my way's fine. Prove this. Prove this. Well, right away you should be careful and say, okay, let's multiply. Yeah, okay, right away I can say that's a difference of two squares. So I could say that's cos, let's call it x, plus sine x, and cos x minus sine x if I wanted to. And then I can multiply both sides. If you doubt that, just go ahead and do it and you'll see that it's true. And then I can multiply both sides by this, and I'm going to get this. One times cos squared is that. One times sine x cos x is this. Minus tan. Yeah, minus tan times cos squared. Remember that tan is sine over cos. So one of the coses will cancel out. You'll be left with this. And then the last one, minus tan x times sine x cos x. Remember that tan x is sine over cos, so you're left with this. These middle terms cancel out, and you're left with sine squared minus cos squared minus sine squared, which is what we had on the left until I made it a difference of two squares. So clearly I didn't have to make a difference of two squares. So left is equal to right. So a lot of these are multiplying out and realizing that tan x will cancel a lot with the cos x. Okay. What about this? There's several ways to go about all of these. Try to remember that tan squared is sine squared over cos squared. And that I can then take sine squared and try to put it over cos squared. Like that. By multiplying it. Well, let's see if I don't have to. Okay, yeah, let's do it. So I can put it over cos squared by multiplying top and bottom by cos squared. But also remember that cos squared is 1 minus sine squared. Let's see if that works out. I don't think that's worth it. Let's skip that part. Let's go back to basics. And we're just going to leave it like that. Let's work on... Okay, let's break this out. Tan x plus sine x. Maybe we should just leave it on the right and focus on the left. How are they Are they the same? Well, sine squared times tan squared is the same as sine squared over cos squared. Fair enough. So that's sine over 4, sine to the power of 4 over cos squared. Let's multiply both sides by cos squared. If I multiply the left side by cos squared, I get cos times tan squared minus sine squared. Remember that tan squared is going to be, and remember that this is cos squared. Remember that tan squared is the same as sine squared over cos squared. If I multiply these two out, when cos squared multiplies this, the cos squareds cancel out. I'm left with sine squared. And when cos squared multiplies the other side, you'd be tempted to say, yeah, okay, we're left with cos squared times sine squared. Okay, fair enough so far. That so far does not equal sine to the power of 4 until we realize that sine squared, that cos squared is also 1 minus sine squared times sine squared. And that therefore becomes sine squared minus sine squared, or minus, open brackets, sine squared minus sine to the power of 4. And then when this minus applies to the bracket, it becomes minus sine squared plus sine to the 4. And these disappear. So suddenly on the left, I have sine to the power of 4. And on the right, I have sine to the power of 4. I'm pretty sure there's an easier way of doing it. We could probably convert, like I was doing, tan squared to sine squared over cos squared, and then make sine squared the same denominator, and then multiply both sides by cos squared to get rid of it. And then the right side will become the same thing. It's conversion of cos squared into 1 minus sine squared times sine squared. Or you can take the cos squared and multiply by the sine squared, and you get sine squared times sine squared. And it'll become sine of 4. Anyway, it doesn't matter. I already proved it once. I don't know why I'm proving it twice. Prove this is equal to this. So this is just a little bit annoying. Well, let's get rid of, let's start by getting rid of denominators. Let's multiply everything on the left, everything on the right by that. Which means we're going to multiply everything on the left by that. You can get rid of all this because this is the last one. Oh, no, it's not. When I meant to multiply everything on the right, try to remember that tan squared is sine squared over cos squared, so that's going to become sine squared. And that's going to become minus cos to the 4. So this is going to be sine squared minus cos to the 4. And this is going to be equal to, when I multiply the right side by cos squared, when I multiply the right side by cos squared, it's going to multiply this, and this, and this. So I'm going to get 1, because cos squared divided by cos squared, minus cos squared, minus cos to the 4. But right here, 1 minus cos squared is sine squared. So something I have left is equal to right. Why is this true? It's going to be very similar to the other one. Because let's keep it the same on the right. Actually, let's convert this. And convert this. This becomes sine to the 4. Multiply both sides by cos squared. This disappears. If I multiply the left by cos squared, it becomes cos cancels out. I'm left with sine squared. And then cos times sine squared becomes this. But try to remember that, try to remember that this is 1 minus sine squared. So that expands and becomes this. This minus applies to both of them. So this becomes minus, and this becomes plus. And these cancel. So you got sine to the 4 on the left and sine to the 4 on the right. That's how you do all of these. It's just math, what do they call it? Math magician, where you're constantly changing things to match. So that was 5, 6, that was 8, 9. Did I do all of them? I don't think I did this one. I did that one. Yeah, I did that one. I didn't do D. Somehow D escaped. Did I do C? I might have not even done C. Yeah, I just did C. D. So again, a lot of it is getting rid of the denominator. So how do you add two things with a different denominator? You cross multiply. And their denominators have to multiply, right? So you get 1 minus cos plus cos minus cos squared. That's a difference of 2 squares. So on the bottom, you get 1 minus cos squared. Guess what 1 minus cos squared is? 1 minus cos squared is the same as sine squared. So that's the bottom. And then you're allowed to simply add, remember that there's an addition between them, 1 minus cos plus 1 plus cos. These coses cancel out. What's 1 plus 1? 2. Left equals right. How do you do other ones? Keep proving, keep proving, keep proving. Prove each identity. So you can see they just want you to. Now, there's an interesting thing coming up. Eventually, for the tougher ones, you're actually going to use quadratics and other tricks. But here, keep in mind that a lot of it's converting tan into its recognizable form. So let's look at this one. A lot of these will be just Pythagoras here. So if I think of tan, it's sine over cos, isn't it? But it's sine cubed. Why is it so big? Sine cubed over cos cubed. Okay, I got to pause. All right, let's continue. Oh yes, why is this the same? So when you multiply cos by sine cubed, cos cubed, one of the cos cubes disappears, becomes squared, and this disappears. So you get sine cubed over cos squared. Then when you multiply both sides by cos squared, you're left with sine cubed on the left, and this on the right. And remember that tan squared is sine squared over cos squared. So the cos squareds disappear. You're left with sine squared. And sine squared times sine is sine cubed. Left side equals right side. B. B is actually very easy. All you have to do is replace one of the coses, or better yet, any of the sines, any of the squares, with 1 minus cos squared. So it doesn't matter which one. So let's just replace the sine squared on the left with 1 minus cos squared. And when we multiply, and when we add 1 to the cos to the 4, we get that. Now, notice we have all coses on the left, so we have to get rid of one of the sines on the right. And when we get that, we get on the right, we have cos squared plus, and if you look at sine to the 4, it's sine squared times sine squared, and that means one of those sine squareds can be converted to 1 minus cos squared. And then notice that we don't have any cos on the left, so we're going to convert. And actually, you know what? Let's just leave this sine squared alone on the left. And we'll just convert one of these sine squares to 1 minus cos squared. When we multiply it by sine squared, we get, let's see if that'll work for us. No, let's convert them both to 1 minus cos squared over here, and up here 1 minus cos squared. So this becomes cos squared minus cos plus 1. So if I multiply this out, I get cos squared plus 1 minus 2 cos squared minus or plus cos to the 4. So that means these cos squared minus 2 cos squared becomes minus 1 cos squared. And suddenly if I rearrange it, left side equals right. Okay, and this is all about cancellation again, but it's almost easier. Oh gee, let's see. What's the easiest? I think this has a truth on the other page. There's this. And then if I multiply both sides by tan x, keep in mind that you don't have to multiply everything in here by tan x because they're not being added. You just have to multiply one of them because they're being multiplied. So you don't have to multiply both. It's not distributive when they're not being added. By multiplying by tan x, it'll disappear. You're left with that. And on the right side, you'll be left with, on the right side, let's do the right side separately. You'll left be tan x over cos x plus tan x over sine x. And you'll quickly discover that that's going to be just 1 over cos x. And that's the same as secant x. Tan x over cos x is going to be the same as sine x over cos x squared, or sine x times secant squared. Good so far, I think. A little bit weird. Okay, let's go back to the left. If I distribute this through, cosecant squared is 1 over cos squared. So if I multiply it through, I'm going to get sine x over cos x squared. Or if you want, sine x over times secant squared. And cos x times sine x is like cos over cos squared. It becomes, one of them cancels. One of them becomes cos, which is the same as secant. So you can see the top left is equal to right. Personally, I think working with the left and the right is the smartest way to go about it. Some teachers don't like that. This, very annoying. Probably the best thing to do is multiply both sides by cos squared b. And that gets rid of it. That just leaves 1 on the right, which is a nice, easy thing to work with. And then we have to multiply everything here by cos squared. Now remember that tan squared is sine squared over cos squared. So the first one's just going to become sine squared. The next one becomes cos to the 4. And the next one becomes sine squared times cos squared. You might say, well, that didn't solve anything. And you'd be right. Except cos squared plus sine squared plus cos squared is 1. So far, so good. Do these cancel out? We'll try to remember that. Let's see if that's working out so far. Yeah, cos to the 4. Oh, no, it doesn't. Because that was not cos to the 2. That was cos to the 4. But remember that cos to the 4 is cos squared times cos squared, which means I can take a cos squared out of there. And I'm left with sine squared. Well, I can't take a cos squared out of there. Never mind. So let's just leave that as cos to the 4. And then this, I think the smartest thing to do would be to convert this to cos, to 1 minus cos. Sine squared is the same as 1 minus cos squared. If I multiply it out, I get cos squared minus cos to the 4. Yeah, that's the best thing. Notice that these cancel out. And that these are 1. So left side is equal to right side. E. This is double angle stuff. I'm going to let it work, or addition angle stuff. I'm going to let you work through it. You got to use your exact values. I don't know why square root 2 cos is there. Yeah, I think you'll discover if you use your exact values for sine of pi over 4, you'll get something with the square root of 2. And this as well. So I'm not going to do those. So how do you do, wow, just endless proof of identity. Let's take the hardest ones, see if we can find the hardest ones here. So these help you for the next chapter. So you should always work on them. Okay, what's the hardest one? This one looks a lot like this. Notice that instead of tan x plus y, if it was both x's, it would be tan x plus tan x minus tan x squared. Which matches that. So right away, we can say that this is 2 tan x, 1 minus tan x. Now we have to prove that tan x is equal to sine x, 2x. And actually, we can say that's not true. That's equal to tan 2x. And tan 2x is never going to be equal to sine 2x. So I guess some of these are not true. So that one's not true. This one, you would multiply both sides by sine 2x. And actually, you'd have to use the double angle formula. I'm not doing any double angle formula stuff. Oh, they're all, actually should not be hard to prove with double angles. Maybe I'll just take one. They're all double angles. Jesus. Okay, so you're going to have to take sine 2x and convert it. Sine 2x is equal to that. So you're just going to replace it. Then you just have to prove left is equal to right. If you expand that, you get, it's like an expansion of x plus y. You get sine squared plus 2 sine x cos x plus cos squared is equal to 1 plus 2 sine x. Now notice that 2 sine x cos x is the same here, and notice this, we can rearrange this. And what's sine squared plus cos squared? 1. So that's proven. So really it's just about replacing the double angle. These aren't too hard. Let's try a harder one. Let's try this. Try to remember that sec t is just the same as 1 over cosine t. And again, we use double angle formulas for the top and the right. I don't know if I want to. Ooh, let's see what's the easiest way to do this one. I think cross multiply. And then realize that it's all over sine t, and that this minus goes up above. And multiply both sides by this. Get it off the right. And now we're going to focus on the left. Try to remember that these are all multiplying. And that this is 1 over cos t. So right away they cancel. You're left with sine t on the right, on the left now. And on the right, you're left with cos t times sine 2t. Oops. So we have to replace sine 2t with what it's worth on the other side. And it's going to be worth this. And we have to replace this. We're just going to keep the minuses separate. We have to replace this with what cos 2t is, and preferably we can use the mixed one. Doesn't matter that it's t. None of that matters. That makes it tough, though. Maybe right now, let's see if we're going to use one that's different. Probably this one. You get 2 sine x cos squared minus cos squared minus 2 sine squared cos squared. So notice that these cancel with this, and I don't believe that's true. It's a weird one. Yeah, so I think I don't have time to go through all that. That's the idea, though. You just keep replacing until you can cancel. Graph, no. Prove your conjecture, no. Copy the chart, no. You should finally be written in the form of no. 8 cos to the 4. That's interesting. So you'd have to reverse that. I don't know. Try 17. So we're talking about a cos 4x and a 2x. Oh my god. No, I'm not going to do 17. That's a huge waste of time. So the next chapter is solving linear equations. Just always go to the summary and look at what the lesson is. Trigonometric equations have an infinite number of solutions. Yeah, always plus the period. Special triangles, a calculator. Yeah, very accurate estimates. Graphing guys, so just use Desmos. And a lot of these will just be proving what possible values there are, knowing your exact values. So this, you should pull up your exact values. Okay. Using the graph, estimate the values. Well, you don't need me for this one. You don't need me for that. That's just, slide. When is y 1? Okay, up here. So that's pi over 2. When is y minus 1 down here? 3 pi over 2. When is that a half? Roughly here in 2 spots. And you have to guesstimate. When is it 0? 3 spots right down at the middle. Minus 1, yeah. Minus 0.5, you'd have to guesstimate somewhere around there. 2 spots. And that is going to have an exact value that you'll find on your table, and it will occur in 2 spots. Like here and here. Same with that. Solve. Okay, this is more accurate. For this, you'll need your exact values. And you have to ask yourself, is this positive or negative? It's positive. What quadrants is sign positive? 1 and 2. Therefore, there's 2 possible values. What are the exact value table? Just pulling them up. Oh, yeah, I'll be right there. Sorry, I got to pause. So once you have your exact values, you can see that sine x, if you go along here, is 3 square root of 3 over 2 for 60 degrees, or pi over 3. That's the only time. However, because there's 2 quadrants, you have to say, okay, this will occur for the acute angle, square root 3 over, sorry, pi over square root of 3. But it will also occur in quadrant 2, which is pi minus pi over 3, which is 2 pi over 3 as the principal angle. So those are the two possible answers. Pi over 3, you're always going to get the acute angle, and 2 pi over 3, which is pi minus pi over 3. That's how you solve all of those. How many possible solutions are there? Usually, almost always 2. The only time there's more than 2 is, or less than 2 is when it's the peak, and more than 2 is when it's at the axis. In which quadrants would you find the solution? Wherever sine is positive, or wherever the question says. In this case, it's where sine is positive. Determine the related acute angle for the equation we did. Determine all solutions. Yeah, so the acute angle's here, and then there's 2 spots where that can exist. Okay, those are all solved like that, and then they just get harder and harder to solve. Okay, so 4. Notice they give you a specific value. They say from 0 to 360. So we're talking this. So your first step is to figure out, where is this angle? Where does negative, first of all, where is cos x negative? Well, it's not in quadrant 1 and it's not in quadrant 4. So it's these two rather, here and here. Hello. Hi, Henry. Yeah.
And Henry speaking.
Yeah, I'm just going to put on my headphones because my phone gets spotty. There we go. Let me guess, this is about vaccines.
No, this is Henry Daly speaking.
Yeah.
No, Bev doesn't feel like.
Okay. Yeah. Oh, well, she asked me yesterday for a lift to get a vaccine. Yeah. Okay. Yeah. When she's lying down, wearing oxygen, does her oxygen stay around 92, 93? Is she on the oxygen right now? Like, is she on the tank? Right. Okay. Yeah. Because if you deprive yourself, yeah, 64 is the heart rate. So 90 is the O2 saturation. So one thing though, when you're short and you spend a long time short, it'll wear you out. Like, you'll get very fatigued. Sure. Yep. Great. So overall, if your oxygen's around 90 or lower, you're gonna get exhausted. Like, you'll feel very worn out. So you won't you will you yeah, 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 okay, yeah, yeah. No, but what can happen is, if you spend the night, I don't know if you spend it with oxygen or not, but if you spend overnight and your oxygen's low all night, you will wake up very fatigued. Um, yeah, and you could still be worn out from the gym 2 days ago. Yeah. So just continue to rest, but do not hesitate to wear your oxygen tank. Yeah, because it's important to keep your oxygen up so that you feel less fatigue. Okay, so you might have heard some of that conversation, but that's okay. I don't care to edit it. I don't have time. So for this case, there's going to be two solutions, and they're going to be in this quadrant and the other quadrant. Determine which quadrant you find them. Determine the related angle. Okay, so the first thing you do is you just take that number, 0.8667, and you do arc sine. You got the trig, second function. Sorry, arc cosine in this case. And I know I used 0.866 instead of the negative, and that's to find the acute angle. So really we're talking about this angle. And to be fair, we can probably just say 30 degrees. And we're talking 30. Well, 30 is the acute angle, which you would find over here. If we're looking in this quadrant, 30 is 180 minus 30. So we're talking 150. And if we're talking the other one, 30 here, that 30 here is 180 plus 30. So we're talking 210. And since we're talking this quadrant and this quadrant, the two angles, if we assume 30, is 150 degrees and 210 degrees. Essentially 180 minus the 30 and 180 plus the 30. And those are the two possible degrees. And there's almost always going to be two answers, except when we're talking about 1, minus 1, and 0. 0 will have three answers, minus 1 will have one answer, and 1 will have one answer. Those are the extremes, like 180, 90, and 270, and 360. And then it continues on. That was 4. And then 5, it's the same thing. This is the exact same method for this. They're giving us a tan value. Notice that tan is the only one really that can have a value that's above 1. And our first step is to say, okay, this is a positive value. Positive value. Where's tan positive? Well, tan is positive in quadrant 1 and quadrant 3. So we should find the acute angle first, and then quadrant 3 will be 180 plus the acute angle. All the quadrants work like this. This quadrant has the acute angle. This quadrant has 180 minus the acute angle. I'm not going to spell correct. This quadrant has 180 plus the acute angle. And this last quadrant has 360 minus the acute. Now just convert that to radians. So obviously for this it's pi, and this one's 2 pi. Determine the solution for the equation to the nearest hundredth. Okay, so we did have to keep the decimals. We did have to keep this. So the real answer is this is one angle where tan is positive, and the other one is 180 plus that, which is 209.92 degrees. So those are the actual answers. And so we knew what they wanted when we saw to the nearest hundredth, which is 2 decimals. All right. Oh wait, I don't think I actually. So that 30 was for the last one. So we have to take this value for tan, which is 2.7553, and we take the arctan. And I should have done it for that was for the answer for the last one. So we take second tan, and we get this 70.05. And since tan is valid in this area, our answer is 70.05. And 180 plus 70.5, which is 250.05 degrees, because they're giving us in degrees. Oh, look at that, it's radians. So now we have to go do it again. So I'm going to just go back to the thing and take tan of it. We have to take this value, we have to fix to radians, and we have to take the arctan. And this is how many radians. So they're giving us, I don't know why they gave us that. Let's try this again. So they're telling us this is 2.7553. And I'm going to go make sure I'm in radians. And I'm going to go arctan. And they're telling me this is how many radians. So this is definitely the first quadrant. And then the second quadrant, when you want to figure out pi plus the third quadrant, when you want to figure out pi plus that, I'm going to put that in memory in case I got to pull it back. You would just add pi value, and that's how many radians. So rounding up here is actually this many radians in quadrant 3, and it's this many radians in quadrant 1. Radians. And if they wanted it in pi, you would simply divide it by pi, and you would put the word pi in front. But I mean, we're not going to do that because they asked for the hundredth, so we don't need to convert to pi. And so determine all possible solutions. So I got to pause because someone's at the front door. So I forget where I'm at, but it doesn't matter because these are just showing you how to solve it. So for this one, there's always going to be 2 possible solutions, and it's always going to be in quadrant 2 and 3. Whereas tan positive, quadrant 3 and number 1. Determine the solution for each of these equations within a 1 full period. So I think I didn't do these, so let's try doing this. Let's see what number's on here. Yeah. So again, you'll always need your exact value table wherever it's implied, and these all imply an exact value if you look at the numbers. So within the first 2, where's tan 1? Tan will be 1 where sine and cosine are the same, because tan is sine divided by cosine. Right? It'll only be 1 where they're the same. The only time they're the same is at 45 degrees. Tan is also only positive in quadrants 1 and 3. So I think we're going to discover it is, if they want radians, yeah, they want radians. It's going to be pi over 4, and let's see, and 5 pi over 4. Let's see if that's true. So where's tan pi equal 1? Here's how you do it. You do arctan in radians, and you divide by, and you see if it divides easily. So we're going to do that. I'm going to pull up radians, clear it, and we're going to do arctan. And we get this weird number. You might say, well, I don't think you're right. That's not pi divided by 4. But if you multiply this by pi, oh, let's see, let's undo that one. That didn't quite go as expected. Let's go back to 1 radians and arctan and get the number back. There we go. It's this number. And you might say, okay, well, is that, what happens if I multiply it by 4? Let's do it that way. And first of all, let's put it in memory. If I multiply by 4, if I get pi, we'll know that this is pi divided by 4. There it is. There's pi. Now let's take pi, and you'll notice that when we just get the radians, it's kind of, oh, it didn't record the right radians. God damn it. So we're going to do arctan again. And we're going to put this in there. Now, if you notice that it's very hard to tell that that's pi divided by what? Oh, shoot. So we got to clear this before we do it. Let's try this more time. Arc10 and put it in memory. Okay, you'll notice right away that that's hard to tell that that's pi divided by 4. So you have to get used to the notion of these things. So if you ever want to see if it's pi divided by some number and you think it's pi divided by 4, you can multiply it by 4 and see. And the other thing you can do is you can divide it by pi. If you divide this by pi, you should be left with a clear 1/4. So let's see if that's true. So if you want to get rid of pi in a radians, or see how many pi radians it is, divide by pi. And we can see a nice clean number. Now, if ever you do have a decimal number and you're not sure what fraction that is, simply hit the 1 over x button. And you'll discover that's 1 over 4. Now, obviously 0.25 is 1 over 4. But you might encounter something like, you might say, some people don't recognize like 1.25. And you have to flip over to discover it's 1 over 8. And some people don't realize that 0.33333 divided by 4 looks like that. And so if you flip it over, you'll discover, oh, that's 1 over 12. Right? So it's a good technique, but when you're given in radians like this, you should divide out pi to get pi radians, and see if it comes out as a nice decimal. So right away we can see, yeah, that's pi over 4. Since it exists in one quadrant, we know that pi over 4 is one answer. And the only other place tan is positive is over here. So that means it's pi over 4 as a acute angle. So that's pi plus pi over 4, which, as I said, is 5 pi over 4. And that's how you do these. So right away, you'll notice that these all fit. Oh, by the way, I could have just consulted my 45-degree angle right here for tan instead of using the calculator, because these are all exact values. So notice that this cosine here is positive, and it gives you square root of 3 over 2, which is here. Right there, an exact value table. Now right away, cosine, and I should just keep this quadrant thing open, cosine is positive in quadrants 4 and 1. So that means we're talking about square root, where is it? There we go. Square root 3 over 2, which is 30 degrees, pi over 6. We're talking about pi over 6 here and pi over 6 here. To figure out this pi over 6, we have to take 2 pi and subtract pi over 6. 2 pi minus pi over 6. And we have to ask ourselves, okay, I got to make the first fraction over 6, so that's 12 pi over 6 minus pi over 6, which is 11 pi over 6. So that's the other one. So we're talking about pi over 6 in quadrant 1 and 11 pi over 6. Now what they're teaching you here is to not have to use a calculator. So it's my mistake using the calculator in the beginning. But I did identify without the calculator it's 45 degrees. If you look at this cosine is negative, so we're talking quadrants 2 and quadrants 3 is where cosine is negative. We can also see 1 over square root of 2 in the cosine list is right there. So we're talking pi over 4. Pi over 4. In quadrants 2 and 3, pi over 4 is here and here. And to figure out the principal angle, we have to take pi and subtract pi over 4, which is 3 pi over 4. And we have to take pi and add pi over 4, which, as we discovered before, is 5 pi over 4. So those are the two principal angles for that. The other three are the exact same thing. You have to find out which quadrant sine is positive in. You have to notice that 1 over square root of 2 is pi over 4. Sine is positive in 1 and 2, so it's pi over 4. It's pi over 4 and pi minus pi over 4, 3 pi over 4. This one is sine is negative, so we're talking quadrant 3 and 4. You have to find where square root of 3 is sine, which is pi over 3. So in quadrant 3, we're talking about pi plus pi over 3, which is 4 pi over 3. And in quadrant 4, we're talking about 2 pi minus pi over 3, which is 5 pi over 3. In tan, it's square root of 3, which is pi over 3. Tan is positive in quadrants 3 and 1. So we're talking about pi over 3 and pi plus pi over 3, 4 pi over 3. That's how you do all of those. How do you do these? Using a calculator. So this is where you have to do the arctan. And remember, they want one decimal place. Oh, so these are worth doing, actually. Okay, so we're going to bring this up. This will not use the exact value tables. Well, it might. Sometimes it might, actually. I shouldn't say not, because sometimes they get tricky. And we have to start with this one. Okay, when is 2 sine equal to minus 1? How do you solve that? Well, we can see right away that sine is being adjusted by a stretch by a factor of 2. You have to just divide by 2 on both sides. So that really means when is sine of x, I'll just use x, when is sine of x equal negative 1 over 2? Notice that negative 1 over 2 is negative, so we're talking about quadrants 3 and quadrants 4. And if we look carefully, we do discover a half on the exact value table right here for sine, which is pi over 6. So really we're talking about pi over 6 as the acute angle. And in quadrant 3, we're talking about pi plus pi over 6, which is 7 pi over 6. And in quadrant 4, we're talking about 2 pi minus pi over 6, which is 11 pi over 6. So those are the two angles for that. So some of these will be on your exact value tables. 3 times cos is equal to 2. Same thing. cos is being multiplied by 3. And what they're trying to get you to do is how to isolate the angle, because that'll become important in some models. So if we divide both sides by 3, we get cos is equal to minus 2 over 3. It is not on our exact value table. And I'm going to use 2 over 3 in the calculator. But I want you to notice that this is negative. So we're talking about quadrants 2 and quadrants 3. So if I take my calculator and take 2, let's just take 2 over 3, just for simplicity's sake, to find the acute angle. And we're going to take cosine, arc cosine. And I don't know if they want it in radians. No, they want it in degrees. So I'm going to take arc cosine, and I'm going to get this many degrees. That's the acute angle, which means in quadrant 2, we're talking 180 minus that. Let's call it this, which is 132.8. And in quadrant 3, we're talking about 180 plus that, which is equal to 228.2 degrees. 2 tan x is equal to 3. So tan x is equal to 3 over 2. That's not on our exact table. But tan x here is positive, so we're talking about quadrant 3 and quadrant 1. So first we're just going to use the 3 over 2. We're going to do arctan. And we're going to discover this angle. And I think they want it to 1 decimal place. So we're talking about this. So that's in quadrant 1, so that's one answer. In quadrant 3, we're talking about 180 plus that, which we get as 236.3 degrees. So that's the 2 answers for that. Now they're all like that. So let me just teach you how to isolate them. First you add 1, and then you divide by negative 3. Now notice this is negative, so we're talking about quadrants 3 and 4. But if you just take the 2/3 and take the arc sine, you discover the acute angle. And then you just take 180 plus that acute angle and 316 minus that acute angle. There you go. Next one, minus 5 cos plus 3 is equal to 2. First, subtract 3. Then divide by 5. So we're talking about a positive cos, which is quadrant 1 and quadrant 4. So you take arc cos. Quadrant 1 will be what comes out in the first one. Quadrant 4 will be 360 minus what you found in the first one. And then 8 minus tan x is equal to 10. Subtract 8, you get minus 1 times tan x is equal to 2. Tan x is equal to negative 1 over 2. That does not exist on the acute angle. Notice it's negative, so it's quadrants 3, 1, no, negative 2 and 4. Take the half, take arctan, that's the acute angle. And quadrant 2, 180 minus the acute. And quadrant 4, 360 minus the acute. That's how you figure out those. What's the next one? Using calculator to determine solution. Okay, it's the same, similar thing. So first you have to say, how do I figure this out? So subtract, get sine x onto the same side. Subtract sine x from both sides. And I'll stop doing this detail. You'll see that these disappear. And this becomes 2 sine x. Divide both sides by 2. Look on your table. You discover, are we in degrees? No, we're in radians. You discover that sine x is equal to 1 over 2 at pi over 6. Notice that this is positive, so we're talking about quadrant 1 and 2. So we're talking about pi over 6 in quadrant 1. and 5 pi over 6, which is, which is pi minus pi over 6 in quadrant 2. They're all solved like that. 5 cos x, subtract 3 cos x, get the square root of 3 on the other side. You get 2 cos x is equal to square root of 3. You get cos x is equal to square root of 3 divided by 2, which for cos is pi over 6. Now, because this is positive, we're talking about quadrant 1 and quadrant 4. So that means we're talking about pi over 6 in quadrant 1 and 360 or 2 pi minus pi over 6 in quadrant 4, which is equal to 11 pi over 6. Cos x minus 1 is equal to minus cos x. Add cos x to both sides. 2 cos x. Get the 1 to the other side. When is cos x equal to 1/2? Well, it's positive, so quadrant 1 and quadrant 4. And 1/2 is the same as pi over 3 in the exact value tables. So we're talking about in quadrant 1, it's pi over 3. In quadrant 4, it's 2 pi minus pi over 3, which is 5 pi over 3. 5 sine x, subtract 3 sine x, you get 2 sine x is equal to minus 1 when you get the minus 1 to the other side. So when is sine x equal to negative 1/2? That's in quadrants 3 and 4, but let's focus on the half. The half is for sine pi over 6, which you were talking pi plus pi over 6, which is equal to 7 pi over 6. And in the other one, we're talking again about 11 pi over 6 in quadrant 4. There you go. Not so hard once you figure out the trick. Using a calculator, now they do it with in degrees. So they're just getting you comfortable doing it in both formats. I don't know why they're going to degrees, because they really don't spend much time on degrees. So here's how you isolate A. Cot x1 is the same as tan x is equal to 1. So we're talking about, since we're talking about, we're still talking about radians. If you look at your exact value, both tan x and cot x, because cot x is equal to 1 over tan. So when is it 1 over 1? Is when tan x is 1, which is pi over 4. Since it's positive, we're talking about quadrants 1 and quadrants 3. So we're talking about pi over 4 and 5 pi over 4. Oh, I see, they're doing the secondary values. When is cos x equal to 2? Well, it's the same as when sine x is equal to 1 over 2. Sine x is equal to 1 over 2 in pi over 6, and that's positive, so we're talking about quadrant 1 and quadrant 2. So we're talking about pi over 6, and quadrant 2 is 5 pi over 6, which is pi minus pi over 6. When is 7 secant x equal to 7? When secant x is equal to 1, which means when cosine x is equal to 1. Cosine x is equal to 1 in only one spot, and that's at, it's in 2 spots, which is at 0 and 2 pi, which is the answer. So secant x and cosecant x equal to 1 at 0 and 2 pi. In this 2 cosecant x, we have to get the other cosecant x to the left side, and this 17 to the left side. We get cosecant x is equal to 2, which means when is sine equal to 1/2? Sine is equal to 1/2 at pi over 6. This is a positive value, so we're talking about quadrant 1 and 2, which means we're talking about pi over 6 and 5 pi over 6. When is 2 secant x equal to 6 minus 1? When it's 5. And when is secant x equal to 5 over 2? When, that's an interesting one. When, to 2 decimal places, so this one won't work out. When secant x, when cosine is equal to 2 over 5, which is equal to 0.4. So we're going to take, notice that it's positive, but we want in radians. Let's try degrees to see if it's a nice even degree first. 0.4, trig, arc cosine. It's not. Oh, we're in radians. Shoot. So we're going to divide by pi. We're going to flip it. Yeah, it's not a nice easy number. Let's confirm it in degrees. (66.42). So we're going to just work in radians then, since they want radians. So we're going to take 0.4 and we're going to arc cosine it, and we get this many radians. And to figure out which quadrant cosine is positive, we're talking about 1. So this is the first answer. And quadrant 4, which will be 2 pi minus that. So we take this, we clear our memory, we put it in memory, and we hit 2 times pi, and we subtract that. And we get this many radians. Now keep in mind they wanted it to 2 decimal places, so it's that, and it's that, and radians. If for some reason they wanted it in pi radians, you just divide it by pi. So let's take this and divide it by pi. So it's 1.7 pi radians. If you wanted to express that as a fraction, it's 17 over 10 pi radians. If you wanted to do this other one in pi radians, it's this. Or just leave it like this for now. And as you can see, that one's harder as a fraction. But if we're going to round up, geez, I guess 29 over 100 pi radians. If for some weird reason your teacher wanted it as a fraction. This next one, 8 cot x is equal to 2. When is cot x equal to 1 over 2 over 4, which is 1 over 2? When tan x is equal to 2. Tan x is not equal to 2. By the way, I don't have to convert when I'm using the calculator. I could have just kept the half. And stayed in radians, gone to trig, and done second degree cot x. And you get this many radians. First of all, when is tan x positive in quadrant 1, which is that? Wow. And in quadrant 3, which will be 1 pi plus that. Since they want decimals, I'm not going to convert it to pi. So that's this. These are radians without pi. Radians can exist in decimals. It's essentially, the pi gets multiplied as 3.14. 8. That's the same 9 we just did. Using a calculator, determine the solution for each to 2 decimal places. So, how do you do that? You have to use the double angle formula. Same with this. You have to use the addition angle formula and this. So I'm going to give you an example, but I'm not doing them. Okay. So in this case, you now have to pull up that information that you had before. So I'm not going to do these in the interest of speed, but you will need this information. And I believe I've kept it over here. Oh no, I've accidentally deleted it. Yeah. So you need this information. the double angle formulas, and the angle addition formulas. We need this. Let's put it on this page. That's the translations. What happened to my double angle formulas? There they are. So going back down to this, 1.5, I think we're at 10. Yeah. How do you solve these? Put them over here. Number 10. First of all, it says use a calculator. So always read well. So they want us to use a calculator. Okay, so how do you solve the first one? First of all, you got to isolate it. So now we know that sine 2x is equal to 1 over square root of 2. Now right away, and actually I don't think I need a calculator in this one, right away we can go to our exact value tables and discover that 1 over square root of 2 for sine is pi over 4. So they're saying that sine double the angle here. Let's pretend for a second that they're just talking about sine of angle A. We discover that that's pi over, what did I just say, 4? That's how old I'm getting. 1 over square root of 2 is pi over 4, 45 degrees. Now, if A is equal to pi over 4, but A is also equal to 2x, we can then say 2x is equal to pi over 4 and divide by 2. And we're talking about the angle pi over 8, 22.5 degrees. So that's how you'd solve that first one. What about this one? Sine 4x is equal to a half, but that looks familiar, doesn't it? That on our exact value table tells me that sine is a half when pi over 6. So if I said sine A is equal to 1/2, you'd say angle A is equal to pi over 6. But A is also equal to 4x. So 4x is equal to pi over 6. Multiply both sides by 1/4. And you get x is equal to pi over 24. So we discover the nifty little angle 30 divided by 4, which is 7.5 degrees, which is pi over 24. So that's how you do these. So far, no calculator needed. Sine 3x is equal to, I think it says no, this time it's not. Oh, these are all equals. These are all equals. So that's the problem with copying incorrectly. Those are all equals. So it's exactly what I'm doing, but I had to not put it on the other side. These are all equals. Yeah, sorry. So the first one, it's the same thing except instead of negative. So let's start again. So there's going to be two solutions. That's the other problem, is I've only done one. So we're going to bring over this as well. We're going to plunk it right in the bottom. Even smaller than that. And we're going to say, okay, the first one, where is sine x positive? Quadrants 1 and 2. So first of all, note that. Second, when is sine A equal to 1 over square root of 2? When it is, look, they didn't even come over well, 45 degrees. So this is figuring out the acute angle, but that means that since 2x is equal to A, 2x is equal to pi over 4. Or x is equal to pi over 8. Well, if you're talking about to 2 decimal places, if we're talking about when is, well, you have to actually use this one here before you solve for x. So one of them is definitely in quadrant 1, pi over 8. But for quadrant 2, you have to take the actual pi first, pi over 4, and say, okay, well, it's pi minus pi over 4. You have to solve it for the pi over 4. And say, we're talking about in quadrant 4, 3 pi over 4. And then you've got to go back and say, well, if 2x is equal to 3 pi over 4, x is equal to 3 pi over 8. So that's the quadrant 2 solution. And it might even still not fall in quadrant 2. But to figure out that you got it right, you go back and put it in your calculator. And you say, okay, if x is 3 pi over 8, we're really talking about 3 pi over 4, right? So I'm going to switch to radians and say is 3 times pi divided by 4. If I take arc cosine, will it give me 1 over square root of, will it give me the angle? No, sorry. Let's go backwards. If I take 3 pi divided by 8 and take the sine of it, and then divide that by, oh, is that 1 over square root of 2? No, it isn't. So let's try that again. Quadrant 2, pi over 4 will be 3 pi over 4. So that's the one I should be doing. So if I take 3 times pi and divide it by 4 and take the sine, there you go. That is indeed 1 over square root of 2. So that means this is correct, which means 2x is equal to that. So x is equal to 3 pi over 8. So you've got to do the quadrants with the full angle before you convert to x. It's a little bit more complicated than I thought. So B, sine 4x is equal to a half. Well, let's pretend it said sine A. Where is sine 1 over 2? We discover it's pi over 3. No, we discover it's pi over 6. Now also, where is it positive? Quadrants 1 and quadrants 2. Which angles are those? Pi over 6 and 5 pi over 6. Okay, now we go back and we convert. If 4x is equal to pi over 6, x is equal to pi over 24. And if 4x is equal to 5 pi over 6, x is equal to 5 pi over 24. So those are the two answers. So you have to do the angles separately. And eventually you'll have to use the double angle formula. Well, if sine A is equal to negative square root of 3 over 2, we're talking about quadrants 3 and 4. And if we look down, square root of 3 over 2 for sine is pi over 4. No, pi over 3. Well, in quadrant 3, that is 4 pi over 3. And in quadrant 4, that is 5 pi over 3. Now that we have that, we can say when is 3x equal to 4 pi over 3? When x is equal to 4 pi over 9. When is 3x is equal to 5 pi over 3? When x is equal to 5 pi over 9. Those are the two possible answers. And notice that x is always positive because we've converted it to the right quadrant. And you always want to find the quadrants before you convert the x. So far, no calculator or double angles. When is cos A equal to negative or 1 over square root of 2? Cos A is equal to 1 over square root of 2 at pi over 4. But we've got a negative value here. So this is quadrants 2 and quadrants 3. What is pi over 4 in quadrants 2? 3 pi over 4. And in quadrant 3, 5 pi over 4. Okay. Therefore, 4x is equal to 3 pi over 4. X is equal to 3 pi over 16. 4x is equal to 5 pi over 4. X is equal to 5 pi over 16. So in E, when is cos A equal to a half? Cos A is equal to a half at pi over 3. When angle is pi over 3. But we're looking at negative, so that's quadrant 2 and quadrant 3. Which means we're talking about 2 pi over 3 in quadrant 2. And 4 pi over 3 in quadrant 3. Which means for this one, when is 4x, is it a half? I forget which one I'm working with. Pi over 3, I'm working with a half. So when is 2x is equal to 2 pi over 3, when x is equal to 2 pi over 6. When is 2x equal to 4 pi over 3, when x is equal to 4 pi over 6. So those are the two values. This is interesting that they keep giving us these half values, but so when is cos A equals square root of 3 over 2? Well, cos is square root of 3 over 2 at pi over 6. This is a positive value, so we're talking about quadrant 1 and quadrant 4. So we're talking about pi over 6 and 11 pi over 6. Which means x over 2 is equal to pi over 6, which means x is equal to 2 pi over 6, which means x is equal to pi over 3. X over 2 is equal to 11 pi over 6, which means x is equal to 22 pi over 6, which means x is equal to 11 pi over 6. And those will all fit. So actually a bit more complicated than I thought. How do you solve this one? A city's daily temperature in degrees can be modeled by this function, where d is the day of the year, January 1st. On days when the temperature is approximately 32 or above, the air conditions of the city hall are turned on. During which day of the year are the air conditions turned on? That's a good one. So notice that they give us temperature, which is over here at y. These are very important to solve. I'm going to go to this page and try to keep it all clear. Here we go. All right. First of all, this graph has been changed to a 365-day period. It's also been flipped on the y. It has not been adjusted left or right. It starts around 10. Y-axis is y is equal to 10. It's going to go up. Well, how does a cosine curve look normally? This, like that. With the flip, though, it's going to start down at January 1st, come up, and go like that. What's the max value going to be? It's going to be 10 plus 28. So we're talking about 38. It would be very good to figure out when it's 0, but they're asking us when it's 32 degrees Celsius. So clearly 38 is quite high. Clearly this is going to be around June, the middle of the year, right? Because the cosine middle is at the peak. And June 30th, let's say, and July 1st will be the peak. So we're going to expect somewhere around June, 20th to July 10th, sort of thing. So that's our first step. Let's find out where that line is hit. So how do we find out where that line is hit? Well, since they give us temperature, we put the 32 on the right side. Now, I'm going to give you a little trick, a really important trick. Inside this, just call it angle A plus 10. Trust me, just call it angle A. Subtract 10 from both sides. Divide by negative 28. We're talking about a negative thing. Simplify if you want. It won't really matter. Where is cos A negative? In quadrant 2 and quadrant 4. Interesting. Where is cos A negative? In quadrant 2 and quadrant 4. So we're going to be talking, that's weird. I would have expected the quadrants right beside each other. So let me just take that again. 32 is the temperature or above. 22, negative 22. So we're definitely talking about those quadrants. Now, let's focus on we're in numbers here. Let's find out this angle, because that's what we're finding out. Let's find out the angle first. Let's find out without the negative number, 11 over 4. I'll show you why, because that gives the acute angle. So we're going to take 11, and we're going to divide it by 4. Don't worry about the pi radians just yet. Divide it by 14. And we're going to stay in, just for clarity's sake, degrees. We're going to hit arc cosine. And we discovered we're talking about 38.21 degrees. Okay? Now, let's just do it once with degrees. And call it 38.21. That is the quadrant 1, because I used 11 over 14. What is that in quadrant 2? Well, that's going to be 180 minus that, which is going to be 141.79. And what is that in quadrant 3? 4. Well, that's going to be 360 minus that, which is very similar, 21.79. And you might say, well, how do I convert that? You're right, that's in degrees. Let's, because we're working in radians, let's convert that into radians. We're going to do it in radians. And we're going to convert it to pi radians to show that it works. First of all, let's find 11 over 14. And you might say, why am I not finding negative 11 over 14? Because that's going to give you the wrong quadrant. It's going to give you quadrant 4. Wait, yeah, quadrant 3. There you go. I was right. It's quadrant 3. Makes sense. It's going to give you quadrant 2. So if I do radian second cosine, it's hard to figure out where that is, isn't it? But that's in quadrant 2 because 3.14 is 180. So that means in quadrant 2, we're talking this. Come on, didn't copy it over. And that means in quadrant 3, we're actually talking 3.14 or pi plus that. Okay. Just use this. There we go. And we'll use this. So these are in radians, right? Radians. So now we have the two angles. We have A. A is equal to those two things. But we really should put those over pi to figure out pi radians. So we're going to take 2.475 and divide it by pi, and we're going to come up with pi radians. And let's start with the 5.616 because it's here. Divide by pi. You'll see why in a second. So the second one is equal to this many, 8 pi radians. And the first one is that 2.75. Oh, I could have just used that. And is this many pi radians. There we go. Now that we have it in pi radians, we can put them both back into the equation. And here's why. And it's kind of stupid because we're ending up solving it. Now that we know angle is this and angle is that in pi radians, we can now put it back. Remember that angle is equal to 2 pi over 365, the converted version. So now we put the first one, 0.7877, come on, is equal to 2 pi over 365. And it's d, so we're trying to figure out d. What do we do here? So it's actually 3 pi over 75 times d. We have to multiply by 365. Best if you don't round up as you go, by the way. So you get that is equal to 2 pi d. We have to divide everything by 2 pi. Well, now you can see that if I divide by pi, I kind of got rid of the pi radians. So another solution, and I'll show you the second solution. So we're going to divide both sides by 2 pi. Both sides by 2 pi. And this will give us day 1. This is the first day. Okay. That's 1. The second one is first you multiply by 365. Let's see if I can go back and find the exact value. And divided by pi. There we go. So first thing we got to multiply by 365. And then we got to divide, open brackets, 2 times pi. Close brackets. And you get, oh, we're getting the same day. Oh, I think I did it wrong. I'm going to do 0.788. Oh, I did the first angle. God damn it. So now you got to do the second angle. My God. Okay. 1.788. 1.788 divided, multiplied by 365, divided by open bracket, 2 times pi, close bracket, equals, and you get this day, I don't know how many decimals I want. You get that day, which is essentially 4th day. Now, except here, why do we divide by pi and then multiply by pi? You could have indeed kept the original non-pi angle with this part of the adjustment. But since you did not divide this, left one by pi, since you did not divide this by pi, you have to get rid of this pi here. Because the whole point of dividing it by pi is so that we can put a pi here that gets canceled out by that. If you do not adjust to pi, you can just get rid of this pi over here. Let's see if it comes to the same thing. Remember 2.475 was this first angle up here. You're going to say, of course it does, because you just multiplied by pi and divided by pi. Now we still have to divide by 2. So that's a little bit off. So can 2.475 be multiplied by 365? And then divided by 2 and give me the same day? No, it cannot. So what happened there? 2.5 pi radians Oh, you had to divide it by pi to get it in pi radians. Yeah, you have to convert it to pi radians. Because if you don't, you're just dividing once by pi radians. And you actually have to end up dividing twice. If you don't convert it by pi radians, oh, yeah. So to convert it to pi radians, I had to divide it by pi. It was a new number that's multiplying by pi. So yeah, you should convert it to pi radians as long as there's pi over here, or you can convert that. Yeah, okay, that's another good point. You can leave it like that, 2.475. You can multiply it by 365. Let's see if that'll work. No, it won't work. You have to convert it to pi radians because you're working with pi radians here. So you do indeed have to divide by pi to get it into pi radians since we're converting to pi radians. Let's see if that's true for the graph though. Sorry, this one's long-winded, but well worth it. So if we put that formula into a graph, just call it f of x, and then adjust it for the ranges that I want to 366 and go up from minus 20 to 44, we get this graph. And we're also looking for when it's 32. And we discover day 143, so I might have got it right, wrong, 221, 143 and 221. Yeah, I did indeed get it wrong. So this is the actual days, which makes sense because 143 converts to roughly, oh, May. And 221 converts to roughly middle of January. So let's see what I did wrong here. Let's go back. It's important to be able to do these. These are the most important questions. So let's see. First of all, just start with the angle. We're going to say, when is 32 equal to minus 28 cos angle A plus 10? First of all, subtract 10. When is 22 is equal to minus 28 cos A? Then when is cos A equal to minus 22 over, or minus 11 over 14? Well, it's negative in quadrants 2 and 3. Okay, so we have to figure out what angle this is, and we're going to work in radians. Maybe I didn't have to divide by pi, actually, now that I think about it. Stupid, yeah, I was already in radians. Okay, so let's just find the angle. And let's take negative 14. There. This will be quadrant 2. And we discover this many radians. And quadrant 3 will be that plus pi. There we go. Let's just work with these. So these are the radians. Now, going to the angle, let's work with this one. 2.4746 is going to be equal to 2 pi over 365 times day. We're going to multiply this by 365 and then divide it by 2 pi. Let's do the second one first because it's in the calculator. We're going to take 5.6162. So go to 2 pi divided by 365 d. We're going to multiply by 365 and divide by 2 pi. Way too big. Way too big. Okay. That should have worked. Oh, I know what's going on. That's way too big. This one's way too big. 3.14. That's not quadrant 3. Oh, yeah. That's not quadrant 3. This here, oh boy, I'm stupid, is the full angle to there. We have to figure out the acute to get to this one, which means I have to take pi and subtract that. Yikes, I should have put it in the thing. Let's go back. Sorry about this one. Let's take 11 divided by 14. Can't believe I botched this. One's a very important one too. We're going to take the arc cosine. But this time I'm going to put it in, why? 11 divided by 14. And we're going to take the arc cosine. And we get that. Let's put in memory. Let's clear the memory and put it in memory. There we go. Now I have to take pi and subtract that to get the acute angle, and then I have to add that to pi to get the quadrant 3. Big mistake. That makes way more sense. So that means we're talking the second angle is equal to that. Let's take that one here, which is already in the calculator, and multiply that one by 365 and divide by 2 pi. Multiply that one by 365 and divide it by, open brackets, 2 times pi, close brackets, equals. Still too big, I believe. Let's see. Oh no, that's it. There we go. So you do not have to put it in pi radians, just stupid me. You just have to leave it in pi. So you get the first one right there. Or that's really the second one. Ugh. Anyway, these are incredibly important to learn, but as you can see, massive mistakes are possible. And we'll just round it up, day 221. The second one, you've got to take this value up above here, and multiply it by 365 and divide by 2 pi. Fortunately, it's in my memory. But multiply that by 365 and then divide it by, open brackets, 2 times pi. So the other day is this. Technically, do it rounded up to 144. But as you can see from the chart, those are indeed the 2 days. So you do not have to divide by pi. You do have to remember to find the acute angle. As working in radians is always a little bit confusing, and you have to convert 3 pi. So if you're doing radians in the number form, you have to be able to understand how it works with the pi. And what I failed to realize is pi is already in the equation, so I didn't have to convert it to pi radians. So there you go. These questions are the ones to master, though. Oh, height in the water wheel, nails, height in the water wheel. Jesus. Okay. Same sort of thing. The height in a water wheel, the nail. If the water is like here, right? The nail's going down. Sometimes the nail's under the water, sometimes it's above. Where t is the time in seconds, and height of a nail is the height above the surface of the water. During what time periods is the nail below the water in the first 24 seconds? So when is it below the water? When is it down here? The water wheels look like this. The water's flowing. It catches the paddle of the wheel, and it spins it. And sometimes like it's big flaps. That's how the old paddle boats used to work. They used to spin these wheels, and these big flaps would push the boat. Very archaic. But a portion of the wheel's under the boat. They want to know what portion of the wheel or the nail is, or the paddle is under the boat. So first of all, notice that this is a sine curve. It's been, let's put that as 2 pi over 8. It's been converted to 8 seconds. How do I know? Because pi over 4 is the same as 2 pi over 8. So we'll get rid of the 2 pi and be left with 8 seconds. So it takes 8 seconds to go around. It's also been pushed to the right by 1 second. Pushed to the right by 1 second. So if you were to think of a normal sine that starts here in the middle, goes up, goes down, and goes up. First of all, let's find the middle. 2.5. Let's assume that's the water. 2.5. Second of all, let's find the height of the wheel. 4. So it goes from 2.54 up, which is 6.5. And then it goes 4 down, which is negative 1.5. Which means that if the height of the water should be at 0, somewhere around there, because 2.5 is not the water; it's the middle of the axis of the wheel. So this portion here, right down here, would be below water, but they flip it. Which means the wheel's going down first, then up. Second, it's still going up to 2.5 and negative 1.5, which means it's 1.5 meters below the water. And somewhere here is the 0. But here's the other thing. They push this thing to the right by 1 second. So if this is 0 seconds, the water wheel starting somewhere on here, coming down. This is not the water, that's the axis at 2.5. And somewhere around here, it's going into the water. Now, right about here is 1 second. And because we figured out it's 8 seconds, it's going to end here at 9 seconds because we're 1 second pushed to the right. So that means at the midway point, what's the distance between 9 and 1? 8. What's 4 off 9? 5. It means it's going to go down at 1 second. It's going to be at the axis, going to go down, and at 5 seconds, it's going to be above. Which means you should expect, this is why I'm modeling this, you should expect your paddle wheel to be meet the water around 2 seconds to 4 seconds. If you get a bigger number, you've done it wrong. That's why I like to draw these things, to understand where I should expect the paddle wheel to be under the water. Good, now that I know that, they want to know what is under the water. Well, under the water here is 0. And you would say, why isn't it 2.5? Because they told us that this height represents above the water. So 2.5 will still be 2.5 above the water. So when is height at the water? When 0. When it's 0. So we're going to do the same thing. We're going to say 0 is equal to minus 4 sine angle plus 2.5. Subtract 2.5 from both sides. Divide by minus 4. Five over 8. Now, that's positive. So we're talking about quadrant 1 and quadrant 2, which makes sense because that's where we drew our wheel. Let's find the quadrant 1 of the angle. And we're talking about pi radians, so we have to work in radians. Clear everything. Make sure you're in radians. And you're going to do 2.5 over 4 if you want. It's the same as 5 over 8. So that's our amount. We have to do arc sine. So this is our first radian in quadrant 1. That's our acute angle. To find quadrant 2, we're going to take pi and subtract that. And you might say, okay, what are you going to do? I'm just going to subtract pi and get the negative value and then make it positive, which is the same thing. If you fiddle around, you'll discover that's the same thing. So that's the other one. We now have our two angles. That's all we want. That's all we want. We can get rid of the other stuff. Get rid of the other stuff. And they're both in radians. Now we bring back the angle formula. Quadrant 1, 0.675132 is equal to the angle. But we said, we converted the angle. The angle is actually pi over 4 times t minus 1. How do we solve this? We have to solve the outside first. So we have to multiply this by 4 and then divide it by pi to get rid of this. Okay, let's do that. Too bad I didn't keep the, I kept the second one. So let's do the second one first. The second one's the same thing. I have to take this and multiply it by 4, divided by pi to equal t minus 1. And if you want to do the whole thing, You just add 1. And that's what I got to do. So I'm going to take this, multiply it by 4, divide it by pi, and add 1. This is our second time, remember, because I started with the second quadrant. So it's telling me that time is equal to that when it's coming out of the water. Now, I'm going to bet that this other time is going to be about, so I guess it's about, yeah, we won't bother with that. So now we're going to take this first angle, which I should have put in memory. I'm going to multiply that by 4, divide it by pi, and add 1 to get this first time as it's dipping in the water. So time 1 as it goes in the water is, time 2 is in seconds. Let's see if we got it right. I'm just going to call it f of x is equal to minus 4 sine open brackets pi over 4 open brackets x minus 1 close brackets twice plus 2.5. Here's our water wheel. I'm going to just give it 1 cycle. Yeah. From 0 smaller or equal to x smaller or equal to 9. And I'm going to put our axis at the 2.5. The x-axis in this case, the x-axis down here, y is equal to 0, represents the water. Because it's height above the ground, and 0 represents the ground or water. So that means it's entering at 1.86, and it's leaving at 4.14. 1.86 and 4.14. And how many, they don't really ask us to what decimal, so you can express it like this, or you can round it up to here, 1.6. You can get rid of that, and get rid of that. And it's in seconds. But we got it right. And that time I didn't flub it. Oops, that's the other one. But you can see we got the model right too. You can see that it's really started here at 1 second. And over there was the displacement of 1 second. It's going down, coming up. There's its max height. There's its lowest point. And that's entrance to the water. So that was a good one. All right, let's keep going. Solve that. Okay. Okay. Interesting one. This is kind of a thinker. I actually prefer these models over anything. They're the most useful thing for university, especially electrical engineering. Okay, so solve that. Okay, you might say, okay, this is for the first 1 cycle. You might say, how the hell do you solve it when they're not equivalent? Okay, that's a good question. X is being adjusted in the middle, and X is not being adjusted on the right side. It's being adjusted by 45 degrees. So when is a sine curve going to be equal to a fractional portion of a cos curve? And how do you solve that? I used to have these quite easily. Cos x, sine x. Excellent. Hang on. Let me just pause this. Okay, here we go. Remember that the additional formula for sine is that. So let's convert this first part into that. So really we're talking about sine x times cos of pi over 4 plus cos x times sine of pi over 4. All we need to know is pi over 4. Well, 45 degrees for pi over 4 is, for both of them, 1 over square root of 2, lovely. Let me confirm that. 45. Yeah, 0.707. So let's use that. 0.707. So if I were to look at that, that's 1 divided by square root of 2. Okay, so we're going to write that. So it's equal to 1 over square root of 2 times sine x plus 1 over square root of 2 cos x. So far, that's the left side. And it's equal, all going to be equal to square root of 2 cos x. We're going to we're going to multiply everything by square root of 2. And if you multiply the left side by square root of 2, gets rid of this, gets rid of this, and it becomes this. If you get sine x to one side, and you put this, there you go. So you subtract both sides. You subtract cos x from both sides. You get when is sine x equal to cos x? When the only time that's true is at pi over 4. However, sine x is also equal to cos x in quadrant 2 at, that's quadrant 1. In quadrant 2, it's going to be equal at 3 pi over 4. In quadrant 3, it's going to be equal to 5 pi over 4. And in quadrant 4, they're going to be equal at 7 pi over 4. Except in quadrant 4, cos is negative, sine is cos is positive, sine is negative. In quadrant 3, they're both negative, so this is true. In quadrant 2, cos is negative. So that's the only two possible answers that exist for that. And if you want to test it out, you can say, okay, I'm going to put, to make sure this is true, is you're going to say, okay, it's when it's pi over 4 plus pi over 4 times 2 times the square root of 2. So I'm going to put the pi over 4 here and here and see if it's true. So what's pi over 4 plus pi over 4? It's pi over 2, which is 90 degrees. What's the sine of 90 degrees? 1. What's the cos of pi over 4? It's 1 over square root of 2. Square root of 2 times that, they cancel, 1. 1 is equal to 1. So that's true. Now you got to figure out if this is true. Well, what's 5 pi over 4 plus pi over 4? It's the sine of 6 pi over 4, which is 3 pi over 4. Okay, that's going to be the same as pi over 4, right? Because that's 3 pi over 4 in quadrant 2 is the acute angle of pi over 4, and it's positive. So that's going to be 1 over square root of 4. What is square root of cos? Square root of 2. What's cos of 5 pi over 4? 5 pi over 4 is in quadrant 3, and it's the acute angle of pi over 4, which is 45 degrees, which is 1 over square root of 2 again. And in 5 pi over 4, cos is positive in quadrant 3, which this becomes, this becomes, oops, phone's ringing, sorry. Okay, anyway, back to this. 5 pi over 4 plus pi over 4 is 6 pi over 4, which is 3 pi over 4, which is the same as this, which gives me 1 over square root of 2. Let's just do that. 5 pi over 4. I'm going to make sure it's in radians. We're just going to do 5 times pi divided by 4. Well, let's add them actually. 6 pi over 4. Then hit the sign. Yeah, I get -1. Interesting. I don't think that's right. 5 pi over 4 plus 6 pi over 4 is, well, plus 1 pi over 4 is 6 pi by 4. And sign it. Okay, I get -1. And then cos of 5 pi over 4, 5 times pi, divided by 4, is that. And then I have to multiply it by the square root of 2. -1. So -1 is equal to -1. There we go. Check. So that's how you can make sure. Sketch the graph of this. Okay, no. That's going to be a period shrunk by half. Nah, you can do that. Explain the value of this function. That's interesting. Explain the value of the function this at x equal to 3 is the same value as the function of x equals 7. Well, you've changed it to multiply these by 2. You've changed it to a period of 100. It's adjusted to the left by 20. It's an amplitude sine curve that's brought down to 55. Why wouldn't it? Why wouldn't the value be the same at 3 and 7? I mean, instead of doing the calculations, I'm going to just graph that and show why. So we're talking about f of x is equal to 25, so that's in it stretched. Pi over 50 creates a period of 100, and plus 20 puts it to the left by 20 and minus 55. And then I'm going to just adjust it way up high. To 25 and way down low to minus 50. And I'm going to go from 0 to 100. Let's see if we can see it. No. Where are you? Okay, I'm going to adjust it again. I'm going to go, oh, it's way down there, sorry. 0, I got the wrong number. 0 to 100 for the x, and 0 to minus 100 there. Okay, why didn't it show? There we go. And we'll just do from here to here. All right, so here's where this. Yeah, 0 to 100. Let's do 100. There we go. And then I'm just going to type in x is equal to 3 and x is equal to 7. And we're going to look at those. There we go. So here's y, and let's just put this a bit to the left of minus 20. There we go, and put this to the right of 80 to show the exact period. There we go. Because it's shifted to the left, and we'll put the axis where it belongs. Because it's shifted to the left by 20, it starts here, goes up, and on the way up, it hits at 3 minus 30.17, and then on the way down at 7, it hits it again. I don't know why they're making this such, why is that crazy? I mean, we could have drawn it and shown, so notice it's 100 long as predicted from minus 20 to 80, because it's shifted to the left by 20, and this makes 100. It's got an amplitude of 5, and its axis is at minus 5, so that means it's going to hit a peak of minus 30 and a bottom of minus 80. Explain why. I don't know. I don't even know why they wanted me to explain that. Create a table like the one below. No. Solve the trigonometric equation this plus sin x. Hint, you may find it helpful to factor the left side of the equation. Factor. Oh, well, I mean, that looks like, oh, I see. Yeah, that's well worth it. 17 and 18 are actually probably worth doing. Ah, come on. Stop doing this. Here we go. So yeah, this is another thing you're going to discover. It's going to come up a lot, is factoring. So if I factor out sine x from this, I get 2 cos x plus 1 is equal to 0. There's two possible answers like any factoring. When is sine x equal to 0? And when is 2 cos x plus 1 equal to 0? Well, this one should be easy to answer. Sine x is equal to 0 at x is equal to 0. Are we in radians? Okay, it's also equal to 0 at pi, and it's also equal to 0 at 2 pi. Because it goes sine comma cos. Oh, actually, sine is cos comma sine. Sine is the y value. So you're going to get a 0 value at 0 degrees, or 0 radians, pi radians, and 2 pi. And this is going to be true when 2 cos x is equal to minus 1, or cos x is equal to minus 2. And then you got to go minus 1 over 2, and you've got to go to your things and discover cos is 1 over 2 at pi over 3, but this is negative. Negative means we're talking about quadrants 2 and quadrants 3. And since we're talking about pi over 6, was it? Yeah, pi over 3 we're talking about. In quadrant 2, that's pi minus pi over 3, which is 2 pi over 3. And in quadrant 3, that's pi plus pi over 3, which is 4 pi over 3. So those are the two possible solutions for that one. So right away, you can see we have 1, 2, 3, 4, 5 solutions. And that's why that one is important. And now finally for this one, I'm not going to go through solving it. It clearly involved breaking down sine 2x. This, I don't think it's going to be that big of a deal. If we go to sine 2x, we're talking about 2 sine cos sine, right? So let's just ask for it. 2 sine cosine. So sine 2x is 2 sine cos. And then you get minus 2 cos squared equals 0. And it's quite clear that you factor out 2 cos x from both. And you get sine x minus cos x here is equal to 0. So it comes down to, when is 2 cos x equal to 0, or when is cos x equal to 0? Cos x is the x value, so we're talking about pi over 2 and 3 pi over 2. And then when is sine x equal to cos x? In multiple spots, so they're both positive in quadrant 1. They're both negative in quadrant 3. And it's always at 45 degrees, pi over 4. So it's at pi over 4, and in quadrant 3, 5 pi over 4, when they're both negative. So we can see 4 answers. Up here, 3 sine x, so it's the same thing. We've got to find a version of cos 2x that has sine in it. So you don't want to convert to that. You probably want to convert to this. So 1 minus 2 sine squared. So you're going to get 3 sine x plus 1 minus sine x squared, right? I think. 2 sine x squared. Okay, now if you rearrange that and multiply it by, all equals to 2, okay? Multiply it by minus. Put sine x squared in front. Bring that minus 2 over. Okay. Let's just make sure I got that right. So you got 3 sine x, and cos 2x is the same as 1 minus 2 sine squared. 1 minus 2 sine squared. Okay, so another way to do it. Let's bring, just so I didn't make any mistakes, let's bring the 2 sine x squared to the right. Let's bring the 1 to the right. And let's bring the 3 sine x to the right. So you get 2 sine x squared plus or minus 3 sine x plus 2. Now, is equal to 0. No, plus 1 is equal to 0. Now let x equal sine x. So really we're talking about sine x squared, 2 sine x, 2x squared, minus 3x plus 1 is equal to 0. What does that look like? That looks like a quadratic, where a is equal to 2, b is equal to minus 3, and c is equal to 1. Now, we can also see if we can figure out a number that multiplies out to minus 2 or plus 2, but adds up to minus 3, and we're talking about minus 2 and minus 1. So we're really talking about x minus 2, x minus 1, and we divide by 2, and we get 2x minus 1 and x minus 1. If I multiply that out, I get 2x squared minus 2x minus 1x plus 1. So that is indeed the factor, which means the two possible factors here are when x is equal to 1 or x is equal to 1/2. Now, remember when we let x equal sine x? Bring it back. When is sine x equal to 1? When is sine x equal to 1/2? Both positive values. So now we can just work with that. Sine x is equal to 1. That's the y value. Only at pi over 2. And sine x is equal to 1/2 in quadrant 1 and quadrant 2. And looking at our exact value tables, 1/2 for sine is pi over 6. So we're talking about pi over 6, and in quadrant 2, we're talking about 5 pi over 6. So that's the 3 possible answers, and you can always go back and plug it into the original equation to see if that's right. But that's how you do that. This is a very important one to learn, the quadratic. And then the last chapter, solving quadratic, there you go, solving quadratic trig equations, which is what 18 hinted at. And a lot of it will be involving letting x equal to something and then solving. Let's see if they give a good one. So they convert I into IO, by both sides by IO, they get this. You got to figure out when is cos theta equal to this plus or minus value, and there's, so that's 4 possible angles because we're plus or minus, and then they show you where those exist. And then you take the arc sine to find the acute angle, 80 degrees. So we're talking about 80, 120, 260, and 280. Only the acute angle is necessary. I don't know why they say that. I guess they're just finding the acute angle, 80. Oh, because it has to do with the angle between polarized material. Yeah, the other 3 angles. Then they're showing you this, right? This is what we did. So they're getting it all to the right side. They're covering this. They're not letting x equal to sine x. I just find it's easier if you solve it as a quadratic as x. You say, well, x is equal to 2, or x is equal to minus 1/2, or sorry, minus 1. So then they do it here, and they come up with the possible values. That's 2 solutions. And then they do it again. So it's like 2x squared minus 3x plus 1. The possible solutions are 2x minus 1 and x minus 1. So sine x is equal to half or 1, and then they do the same thing. There's two possible solutions. And sine x equal 1 has one possible solutions, then they add it all together. Then they graph it. You can make sure on the graph. Then they do the same thing here. Now the interesting thing about tan x is you have to convert sec squared into a tan version, or you could convert tan into a sec version, but the easiest is sec squared has this equivalent. Then you put it in a quadratic, and so it'd be like 2x squared plus x minus 1 is equal to 0, and you solve. And these are very handy. So here we convert cos x into a version of sine squared, so that it can become the this quadratic 6x squared minus 3x minus 1. And then here they even use the quadratic formula because there's no pure factor. So you have to be able to use the quadratic formula. And then you've got to convert it into radians and remember to do the stuff I was making. Then they just give you a whole bunch of examples. Some of them involve converting some versions into others, like here, that's just straightforward quadratics. But here you'd have to convert. And you'd have to convert a 2x into a cos x. So you want something with just cos squared in it. Here you'd have to convert a sine x or the cos x into something with sine in it. So there's a sine squared in there. Here you'd want to convert this cos 2x into something with cos in it. And this cos 2x into something with sine in it. And it always comes down to quadratics. This is just figuring out b. And I would solve it maybe as a quadratic function. When is sine x squared equal to c? Oh, they're showing you where c is, are they? Oh, they're showing it. So what does c do? It lowers it. So you just figure out where the... Oh, yeah. So, no, you'd have to factor it. So sine x plus c, sine x minus c. And then when is sine x equal to... Or sine x equal to square root of c and sine x equal to negative square root of c? Yeah, it's a good question on that one. And then they review the chapter. So I'm gonna come back to that one. But that's all basic quadratics. And I'm just gonna stop, and hopefully this review of the chapter helps you.